Hello? Oh, no, Joaquin.
So Stanford High School, as you of course know, is a part of Stanford University, while it is an independent school accredited by itself. But of course, it relies on a vast amount of resources made available to us by Stanford University. As you know, as a part of our strategic plan, we are trying to further utilize Stanford's academic resources. And our faculty director of Stanford Precollegiate Studies, Ray Mazzio, has been making active efforts to connect Stanford High School with other units and organizations at Stanford University. So, Ray, please welcome Ray Mazzio, who is going to
I was told to stand over here. So it's a real pleasure to welcome all of you here today. Really pleased to see all this, great interest in activity. So I'm really happy to introduce today my colleague in the mathematics department, Tadashi Tokieda. I think that, as Tomohiro said, we're trying to share with online high school all the wonderful things that Stanford has to offer, and we have people who, do remarkable things. It's a real pleasure to know people around Stanford who contribute so much to the world in many ways, and Tadashi, I think, is rather special even in that elite crowd. So he grew up as a painter in Japan, and he became a classical philologist in France. And he switched to mathematics, so he had a rather peripatetic and remarkable intellectual trajectory. He got his PhD at Princeton a few years ago, and he was at Cambridge University as a director of studies in mathematics for 13 years, and we appointed him to a professorship in mathematics just last fall. Has wide-ranging interests, obviously intellectually and in outreach too, which I think makes him particularly well-suited for speaking with us today. He's very active in various things, in particular in outreach in the developing world, especially in African countries and at the African Institute for the Mathematical Sciences, which is near Cape Town, South Africa. So without further ado, let me introduce my colleague Tadashi Tokieda, who, as you can see, has adapted very well to life in California.
As we go through life, we encounter numbers that look significant. For example, do you recognize this one? What's that? 3.1415. What is it? Pi. Yes, you are right. That would have been pi if that digit had been 7 instead of 4. And then the next one, what about this? 299792458. It's one of the universal fundamental constants of physics. Indeed, that's the speed of light in vacuum in meters per second. And every once in a while, though, I run into a number that rings a bell, but which I can't quite place. For example, faced with this number a week ago, I knew that it was significant in my life, but I couldn't remember where it came from. So I do a few calculations. I mobilize my entire scientific erudition and sophistication. Days pass. I still don't see it. But finally, eureka, yes, of course, that's the telephone number of Stanford Online High School. So the leitmotif of this talk is that number there, 2.5. And I'd like to somehow persuade you that 2.5 is very significant because it is a number between 2 and 3. 2 and 3, because that's the dimension, metaphorically speaking, where paper, sheet, membrane, surface, anything of that kind evolves and continues to surprise us by various phenomena. Indeed, by itself, intrinsically, as we say, a paper has dimension 2. It's a two-dimensional object, but also it will be very, very important that it lives in an ambient three-dimensional space. And that interaction between intrinsic and extrinsic is the leitmotif, indeed, of display. So in order to illustrate that point, I'd like to begin by a magic trick. Here is a coaster that I brought, a disc-shaped thing from home, and then a sheet of paper with a hole, square hole in the middle. Now, when I fold this paper, I can pass the disk through that hole. Yeah. It can go through in the reverse direction as well. I haven't started cheating yet. It is really going through. And yet, when I put these next to each other, clearly the diameter of the coaster is larger than the diagonal of the hole. I didn't stretch, let alone tear. Well, it does actually go through, you know. It is going through. I fold it like that, and then, you know, it is going through. What is going on? Because I'm very happy to meet you this morning, I'll give away the secret for free. In case you want to do it with family and friends later on. When I fold this paper like that, that's kind of a two-dimensional fold. The largest gap that I can take advantage of is only this gap, which used to be the diagonal of this square. But that's not where I stop. I grab this and start twisting the whole thing. As I twist, you can see that part of the paper starts lifting into the third dimension. It escapes into the ambient additional dimension. And I twist it until those two edges are aligned, and then I squash and fold, and I have to shift by one. In that configuration, the gap that I have created is no longer the diagonal, but what used to be the sum of those two sides. And if you remember Pythagoras, you've gained the square root of 2 factor. That's a little bit more than 40%. So the secret of success is to make a hole which is shorter, indeed, whose diagonal is shorter than the diameter, but whose sum of the edges is a little longer. Yeah. Okay. And you see that this was successful what seemed impossible became possible because you had this escaping into the ambient dimension, and you could come down. And often this is a pattern in science that by having this extra degree of freedom, people think that higher dimensions are harder, but sometimes they make life easier. And by passing through there, you can make things easier down here. Do you recognize this character? He's one of the most romantic figures in the history of mathematics, and he looks rather sad and indeed romantic. Who is this? Yeah, do you recognize? That's right, he's Galois, and who died at the young age of 20. And in so same, Professor Matsuo will say, Tadashi can't do arithmetic because if I subtract 32 minus 11, it is 21. But he died shortly before his 21st birthday. And he left a gigantic legacy for us to chew on. And one of the problems that he taught us how to think about in the correct fashion goes back to the Greeks. You probably have the experience in high school of drawing some geometric figures using straight edge ruler and compass alone. For example, if you have an angle, you can always bisect it in two parts. Yeah? So how can you draw a line so that it divides the angle into exactly two equal parts? And the Greeks wondered, can you do the same thing into three equal parts? To be sure, there are, of course, angles that you can divide into three parts. For example, the flat angle 180 degrees, you can divide that into 60, 60, 60. That's no problem. But that's a special example. Is there a general algorithm that solves the problem of trisection, as we say, in general? And one of the things that you learn at university when you take, for example, Galois theory, and in fact field extensions, is that no, you can't always do this. There are examples that you cannot trisect with ruler and compass alone. For example, an innocent-looking number like 60 degrees is impossible to trisect. However, there is a traditional and ancient Japanese art called origami. Ori means fold, and kami means paper. And you probably have seen some artwork. And using origami, you can actually trisect an arbitrary angle. And indeed, intersect an arbitrary angle. And once you believe in the possibility, it's actually not too difficult. There are several different constructions, and this is my favorite one. Here, let's revise how you would bisect an angle by just folding a sheet of paper. That's easy, right? So imagine that you have an angle given as a corner of a sheet of paper. Usually the corner of a sheet of paper is 90 degrees. But suppose that you created an angle there in the corner of a sheet of paper. Yeah? And how do you bisect it? Of course, you fold it in two, and arrange those two edges to aligned, and then you just crease, and when you open, you have this beautiful line coming out of the corner, which is the bisector of this angle, divided into two. Yeah. Well, trisection is no harder. If you have an angle, you just fold, but you overshoot, and then you come back, and you make this pleat, folded pleat, and you just align those edges, and you negotiate, and you do it continuously. That's the strength of the origami construction. And when they're aligned, you crease, and when you open, you have two beautiful lines coming out of the corner, and those are trisectors. And n is the same thing. You go back and forth, you take a pleat with n folds, and then you just arrive, you do that. Okay. So that's one Greek problem disposed of. Do you recognize this next character? He looks rather austere and less romantic than before. That's Gauss. Very good. You are cultured people. So Gauss lived rather longer, and he too left us a lot of legacies, and which are still thriving and flourishing today. And one of the problems that he taught us how to think about correctly and in a civilized fashion is a similar Greek problem. So you probably have drawn with ruler and compass again, regular polygon. For example, regular triangle, that is an equilateral triangle, can be drawn in the following fashion. You just take a segment and you make a whoop, whoop, those compass constructions, and where they intersect is the vertex that will complete the equilateral triangle. And the question was, well, can you do it for all n? In other words, for which n can you draw with ruler and compass only a regular polygon of n size, regular n-gon? And as you imagine, Gauss taught us that you can't always do this, and the n has to be actually a very, very special kind of number. And the statement is a bit complicated, but the key part is this number there. 2 to 2 to small n plus 1, these are called Fermat primes, and these are, if these are primes. And n must have this very, very special number. So it has to be a product of those different things. So here underneath, by plugging in various values with this small n, I produce those bold-faced numbers. So 3, that corresponds to when n is 0. You see, 2 to 0 is 1. So 2 to 0 is, so 2 to 1 is 2, 2 plus 1 is 3, and so on. So 3, 5, 17, 257, those are Fermat numbers. And you can also take products of these, but remember, distinct products. For example, you're not supposed to do 3 times 3, because 3 and 3 are not as distinct, but 3 times 5 is okay, so that's 15. 5 times 17 is okay, and that's 85, and so on. And also powers of 2, that's easy, because you see, once you have constructed, let's say, a regular 17 gon, well, you know, as we discussed, it's easy to bisect each angle. So you can double the number of sides. Well, that's cheap. So you can always double, double, double. So powers of 2 in front, it comes for free. Yeah. So those are the only numbers, so the only ends that you can achieve construction for the regular n-gon for. However, you're beginning to suspect at this stage that with origami, you can do all n. So let's give you a demo. First, I'll do a regular 5-gon, regular pentagon. 5 is not all that impressive because 5 is there, but this will illustrate the general idea. What you do is you take a straight strip of paper, and you tie the simplest knot you can possibly imagine. So that's that. Okay. And then, having tied this knot, you tighten it and flatten it at the same time. You just keep negotiating. Tighten and flatten, tighten and flatten, tighten and flatten, tighten and flatten. And eventually, when it's completely tight and flat, you obtain a knot, flattened knot like this. And in order to show you what's going on, I'm going to throw away this stuff that's sticking out. And you see that what you have created in the middle is a very beautiful regular pentagon. The beautiful, I said, but the beauty of this construction is that I didn't have to think. Nature took care of everything. It's automatic. Good. Well, that was the regular 5-gon. And you agree that I made a simple pass through the knot. I created the simplest knot, so just one pass. Suppose that I make 2 passes through the knot. Well, you have to do it in a certain systematic manner, but I'll show you a picture in a moment. So 2 passes. It turns out that if you make a knot with 2 passes, and then flatten and tighten it, you get the regular 7-gon. 3 passes, regular 9-gon. 4 passes, regular 11-gon, and so on. So all odd numbers can be accessed that way. By the way, this is by no means my invention. If you are lucky enough to visit Japan, I'm advertising tourism in my country, and stay at this traditional inn called ryokan, they usually lend you a pyjama, a very nice soft pyjama, and that comes with a soft belt that you tie around. And then you can sort of put it on and go for a walk in the town and so on. It's a really beautiful way to spend the summer evening. But anyway, that belt is traditionally folded in a pentagonal pile and offered to the guests. So this goes back a long, long way. But the construction, as I say, can be generalized to any n. And so here are the basic pictures. That's a regular 5-gon that you saw already. And the regular 7-gon looks like this. So you have that kind of pattern. And so on, so on. So 7, 9, 11, so all of those odd numbers can be achieved. And as I explained, once you have all the odd numbers, bisection is for free. You might be wondering, wait a minute. So there is one more regular odd gon that we're missing. How about n equals 3? Yeah? Can you do a equilateral triangle with this construction as well? Well, what do you think? 1 pass gives you 5, 2 passes 7, 3 passes 9. How many passes do you have to make in the knot in order to go to achieve n equals 3? 0 pass, and that's the construction. So you go in and you try to make a knot, but don't quite manage and come out. And that in that behind that corner, there's an equilateral triangle hiding. So this does work in all cases. Okay. So far, we have been discussing geometry and pure mathematics, so to speak, and I can't really tell the difference between pure and applied. They're all the same. But we'll now transit gently into physics, and later on, rather surreptitiously, going to engineering, physiology, and so on. We'll be expanding the field of our investigations, and we must enlarge our field of investigations because the phenomena in question exist on all scales across the universe, all over the place. We can't limit our investigation artificially. And depending on whether they come in a designed fashion or randomly created, they come under different names. For example, origami is the designed end. You have to do everything deliberately. And at the other end, random end, it's just crumpling a sheet of paper. It's basically a randomized kind of origami. And in the middle, there's this fundamental concept called buckling. What is buckling? You know, if you take a rod like this, and then try to compress the ends. For a small amount of compression, very weak compression, this rod becomes a little shorter. It's barely visible. But at some critical load, it can't take it anymore, and boom, buckles out by a large deflection like this. So this kind of instability, as we say, is called buckling, and that is really the grandfather or grandmother, as you like it, of all this range of phenomena. For example, in the top left corner, I show you a picture of what is called Minori. So it's from a region of Japan to the west of Kyoto. And what that is it's a special way of making paper. So you take a sheet of paper, and then you wet it, moisten it, and then you stretch it with persimmon. And having put persimmon all over the place and stretched out, you dry it. And then you crumple the whole thing and moisten it. And then you stretch it out with persimmon again, and then dry it, and then moisten it and crumple it. And you keep doing this. And this act of repeatedly rubbing it with persimmon puts a lot of fibers and intermeshes the paper fibers so as to make the paper really strong. So strong, indeed, that you can make, for example, clothes, shoes, bags out of this paper. And it is a very useful thing. And the key behind this is that all those crumples or wrinkles, if you like, are happening on the scale of less than a millimeter, very, very fine crumpling that are used for strengthening the material. On the top right corner, there is a very nice animal there. And you see that his trunk is lined with various wrinkles, and they are the best of thermal and biomechanical reasons why biological universe takes advantage of wrinkles all over the place. Yeah. So those are wrinkles, if you like, on the scale of centimeter to a meter. That's our scale. And then those wrinkles, origami, can happen on a completely gigantic scale. For example, look, this is a map of Latin America, and the backbone of it is called the Andes mountain range. What is Andes? Well, it's none other than this. You have the Latin American plate, and then the part of the Pacific, it's called Nazca plate, started pushing against it. And when you push against some sheet, what happens? This happens. It starts rising like that. And that is exactly the Andes. What happened in the similar fashion in Europe is the Himalayas. Africa pushing against Europe, and of course, everywhere else in the world. The Alps is Europe, excuse me, Himalayas is north of India. Okay, so Indian subcontinent pushing against Asia is Himalayas, and in the Alps, that's Africa pushing against Europe. Okay, so this kind of huge thing is also an origami, and that's happening on a scale of kilometers, maybe thousands of kilometers, and so on. By the way, I can't resist the temptation to insert a little anecdote about this. You know that the Amazon is probably the greatest river in terms of the water flux in the world. It flows into the Atlantic towards east. Yeah? You know that it used to flow into the Pacific towards west in the other direction, but Andes started rising, and then eventually it tipped the gradient in the wrong direction, and everything started flowing in the other direction. And it happened quite recently on the geological time scale. Wonderful things. Okay, good. So all those things are happening on all scales. And the challenge is, can we extract science out of all this huge variety of phenomena? For example, here I show you a picture of a crumpled sheet of paper. Can you see some laws of science, patterns of mathematics, that govern even a crumpled sheet of paper like this? And that picture, by the way, looks like a crumpled sheet of paper for the good reason that it is a photograph of a crumpled sheet of paper. Thank you very much. But let me rephrase the question. What is it that we're seeing? If, for example, you ask an unskilled, and in fact a skilled artist, to draw a crumpled sheet of paper, you'll see that that's a very, very difficult task. Very few people can do this. That's because, you see, a crumpled sheet of paper is a bunch of points and connecting lines, if you like. Or if you like, mathematicians will say vertices and edges. But not all of those network patterns on a sheet of paper arise out of as a result of crumpling a sheet of paper. There's something very, very special about those networks that can be created by crumpling a sheet of paper, and which we instinctively and unconsciously know because many of us have lived in this universe for a long, long time, some of us longer than others. And we know, but we haven't yet begun to verbalize, let alone use, what these laws are that we know internally. So artists can't do it, yeah, but nature can. So what are these? I'd like to give you a present today, and a present that you can take home. Here is that's not the present, but here's the lion that I folded. And when you open it, that is the fold pattern on the sheet of paper in the square sheet. Don't worry too much about blue and red. Those are the ridge and valley folds. But what is interesting is that in this pattern, there are lots and lots of lines coming into various points, right? So edges coming to various vertices. And some of the points, for example, this one has 4 lines coming into it, 3 of them blue, 1 of them red, yeah? And this one has 4, this one has 4. This one has as many as 8 lines gathering there, and here you have 6 of them gathering, and so on. It turns out, and this is a theorem, that around each vertex, around each point, you can have only an even number of lines coming in if you crumple a sheet of paper and squash it. So here's what we do. You take a sheet of paper, crumple it, and in order to make the discussion a little more convergent, I'm going to squash it onto a plane and then open it. And the question is, what are we seeing? And in a fold like this, or even if you do it deliberately, you have always an even number of edges coming in. Let me show you one simple example. A fold that everyone uses every day is what the origamists call the square fold. I just do that. And then what you see is those 4 lines coming in. I'm going to trace them so that you can see that they're all 90 degrees, and there are 4 of them. Okay. That theorem, that there are only always an even number coming in at the any vertex, is not too difficult to prove, but it's a bit tedious. So let me skip over that, and please believe this. For the experts, what we're really doing is when you squashed it, you are creating what you might call a singular covering space, and then covering space, and there's a pattern of front, back, front, back, front, back, which forces the parity issue. Anyway, what I would like to then discuss is the following. Since always an even number gather around the vertex, the simplest pattern looks like this, just 4. The next in simplicity is 6 and 8 and so forth. So that kind of thing can happen when you don't pay particular attention to what you're doing, and you just fold in a random fashion, and that's what you get. I'm going to trace this random pattern, that, and that. There are 4 vertices, 4 edges coming in. Okay. I have created 4 angles, alpha, beta, gamma, and delta. Okay? It turns out that those 4 angles cannot be arbitrary. They satisfy some law. Number 1, they have to add up to 360 degrees. Well, you wish that you said it first, but I did. Okay. That's the easy part. Number 2, it turns out that the opposing angles, pairs, alpha and gamma, and beta and delta, must have the same sum. In other words, alpha plus gamma equals beta plus delta. And that's certainly satisfied in the 90-degree case, right? 90, 90, 90, 90, it's always the same. So the theorem is that. And those 2 conditions, that they add up to 2 pi, 360 degrees, and that the opposing angles add up to the same, are necessarily sufficient for that corner to be manufacturable by flattening and crumpling a sheet of paper, crumpling and flattening a sheet of paper. The theorem goes back, is usually attributed to Kawasaki, but I found somewhat earlier sort of allusion by a Japanese physicist called Fushimi and so on. In particular, the kind of picture that I drew there is not manufacturable by crumpling. It's absolutely impossible, however clever you are, because the sum of that thin edge together with this large sector is far too large compared with the sum of the other 2, right? So it violates that law. Now, I'd like to give you a proof of this. In order to do so, let's go back to how this thing was manufactured. It was like that, yeah? That's angle alpha. Seen from the other side, it's also alpha, but that's beta plus delta, oops, minus gamma. Did you understand that? No, I didn't. So let's do that again. So that's alpha, yeah? And if I turn over, that's still alpha, seen from the other side. But you see, this angle alpha consists of the overlapping beta and delta, and what's the overlap that we added too much? Gamma. So you have to do beta plus delta minus the excess gamma. That should equal alpha, and that's exactly equivalent to what we wrote there. It's alpha equals beta plus delta minus gamma, QED. In general, what you have is an even number of edges coming in. For example, let's call them alpha 1, alpha 2, alpha 3, all the way to alpha 2n. For example, alpha 8 or alpha 16 or alpha 14 or something like that. And it turns out that these are realizable by crumpling and flattening a sheet of paper. if and only if those two conditions are satisfied at the same time. So the first one is easy, but the second one is quite curious. It says that alpha 1 minus alpha 2 plus alpha 3 minus alpha 4 plus minus must close to 0. This kind of thing is called the alternating sum, and it appears very often in mathematics in an area, in a technique called homology, and this is really a discrete version of the homological constraint, it turns out. Okay, so you see this simplest case of 4 could be written like that. Instead of that, you can say alpha minus beta plus gamma minus delta equals 0, right? Okay, and the proof is the same. So if, for example, Dr. Hoshi throws at me an even number of those numbers that you want to realize as angles of this, those sectors, well, he's probably not going to give them to me in the correct order. But there should be some permutation of these, or rearrangement, reordering of these, so that they add up, first of all, to 360 degrees, but also in that rearranged correct permutation, the alternating sum closest to 0, then I can realize them in the following fashion. I take the largest of these and start folding back and forth, back and forth, back and forth, back and forth. And when I run out of the supply of the angles, I know, because of that closeness condition, that I also run out of, I close exactly, and then I crease and open, and those are the angles. Okay. So that's the general construction. But that takes care of the local geometry. But when you do globally, that is, when multiple vertices start talking among themselves via edges, then stuff starts getting really interesting. And the big picture is still unknown. Several of us are thinking about this kind of thing, and something called a discrete version of Gauss-Bonnet starts making its appearance and so on, but we still don't know how to characterize these crumpled sheets of paper. Well, we'll now move really into serious physics. And do you recognize this person? He's probably less famous as a portraiture as the other two. Does anybody recognize this? You run into this man, Simon Denis Poisson, all over the place when you learn mathematics. You know, Poisson equation in gravity, and you know, Poisson process in probability, and Poisson bracket in quantum mechanics and the classical mechanics, and Poisson this and Poisson that. And today I'd like to teach you something about Poisson, something else about Poisson. There is a beautiful and very useful area of physics called elasticity. And my challenge is to teach you half of the theory of elasticity in about 40 seconds. Here we go. Let's take a block of material and imagine that I squeeze it in this direction. Well, what do you think happens? In the transverse or perpendicular direction, it's going to bulge out a little bit in response, yeah? How much it bulges out per how much I squeezed in is called the Poisson ratio. More rigorously, you have to take the derivative. Or, equivalently, I can pull in one direction, and what do you think? It's going to tuck in its belly, and the girth will become shorter. How much it went in per how much I pulled out, it's the same thing. It's called the Poisson ratio. Now, in the literature, scientific literature, the notation, you see the symbolism is very important. Notation for Poisson ratio is a mess. I mean, some people denote it by sigma, other people denote it by lambda, which is a disaster because it should be really Lamé constants. And the kappa, people who should know better denote it by p, and so on and so on. Yeah, there is absolutely no consensus. It's terrible. And after many years of deep thinking, I finally came up with the God-given, or rather Tadashi-given notation for Poisson ratio, and it should be this. It's alpha with a dot. Okay. So in 200 years' time, I would like the history of science to remember me as the person who finally discovered the right notation for Poisson ratio. Let's train our intuition by some examples. Here is, if you like, a gadget that I made with a Meccano model. Those greenish rods are supposed to be rigid rods, and those black dots are supposed to be hinges, or universal joints, okay? And if I make a model like that and squeezing along the blue arrows, you immediately see that it's going to expand along the red arrows. That's a Poisson ratio behavior, so lateral response when you sort of do something stress in a certain direction. So if you assemble these into a structure, you get some mesh pattern like that. That's already useful. For example, if you design it in the designing of a clothes, you have something which, when you stretch in one direction, it hugs your body very, very tightly, and then it's very thermally insulating and so forth. Or you can do it with a basic unit cell, which is a hexagon, and you collect them into a beehive pattern, and that behaves in the same way. So it's always reckoned positive in that case. Okay. Throughout those examples, you recognize that actually Poisson ratio varies a lot from a pattern from structure to structure, but there is one traditional belief that everyone subscribes to, and that is Poisson ratio should always be positive somehow. That is, it's a bit absurd to think that there exists a material which, when you compress, starts sort of shrinking in all the other directions as well, right? Okay. But if you think about it, there are some things in the world which actually have a more or less 0 Poisson ratio. For example, if you take a spring, I'm not sure the spring is the best example, but if you take a spring and shorten it along its length, it doesn't look like it's getting any fatter in the other direction. But actually, if you look really, really carefully, it is getting a little fatter. So the Poisson ratio is almost 0, but strictly speaking, with great measurement, you can see that it is positive or the same. Faced with something like this, you turn to some authorities, and this is, I don't know why it's in French, because that's the copy that was lying around in my office. The Landau was a great Russian physicist, and he created a powerful school of theoretical physics in Moscow, and together with his student Lifshitz, they wrote what is the Bible of theoretical physics, called the Course of Theoretical Physics, in 10 volumes. And every person uses this. If you walk into any practicing theoretical physicist office in the world, whatever the language, you'll see several volumes of Landau Lifshitz in translation in the office. And I certainly use all 10 of them more often than any other book. And volume 7 turns out to be dedicated to the theory of elasticity. And there, you see, Landau is preaching to his students, and all the students have donkey ears and so on. But anyway, so on one of the pages, there is a footnote, which I'm going to read out and translate in real time. It says, in fact, the Poisson ratio varies only between 0 and 1/2. We don't know of anybody in nature for which sigma, that is the notation for Poisson ratio. But do you know a good notation for Poisson ratio? Thank you very much. Yeah, that's alpha plus dot, right? Poisson ratio should be negative. That is, which would bulge out while being pulled out. Okay, it's natural then to be tempted to produce examples with negative Poisson ratio. And once you believe in the possibility, it's actually not too difficult. So here is a hexagon. You remember those beehive patterns and so on? Here's a hexagon, but now a dented concave hexagon, not a convex hexagon. And if you make a pattern like that, you can feel, can't you, that while being compressed along the blue arrows, it's going to shrink along the red directions as well. That's negative Poisson ratio behavior. And you can assemble them into a pattern and create something. There are other ideas for doing this. Here is a picture of various squares that are just stuck together, but they're together linked in an interesting hinged pattern here. I drew a halfway picture. You see those squares, as I pull various directions, start rotating left, right, in an alternating fashion, and they together dance like this, they open up in all directions. Isotropically, as we like to say, isotropy means that in all directions it looks the same. There is no preferred direction. Yeah. All equal sort of behavior in all directions, isotropic. And you can do it with triangles and so on, and there are 3D versions available as well. And so it's not true that the Poisson ratio for isotropic materials, so materials that don't distinguish among different directions, that don't have direction dependence, it's not true that it's always between 0 and 1/2. On the contrary, the true statement, it turns out, is that it's between -1 and +1/2. Those two limits, both limits have a physical significance. For example, let's discuss this limit, 1/2 there. That's the limit of incompressibility, not to be confused with incomprehensibility. So what it means is the following. Let's say that you have a material which does not change its volume, however hard you compress. It just doesn't change its volume. Yeah, there are materials that more or less behave like this. And you squeeze it in one direction by, say, 1 unit distance. Well, there are 2 remaining directions into which the material can escape. Yeah? So you have to go 1/2 and 1/2 in order to compensate for -1. And that's why you get 1/2. So in a higher dimensional space, for example, in dimension D, the limit should be 1/d-1, if you like. Yeah? Okay. So, and that's the incompressible limit. Or an alternative way of saying this is that compression has to do with a pressure wave. A wave through a medium can traverse in 2 different ways. You can have sort of compression like this, and it bounces like that, and that bounce compresses the next material and bounces like that, and that compresses the next bit and bounces. So you can have a wave traveling like that. That's called a pressure wave or P wave. Another pattern is this kind of thing. But anyway, so this 1/2 means that if you have Poisson ratio 1/2 isotropic material, and when you send in a compression wave, it travels infinitely fast. And that you can't do. Anyway, that's a wall you can't go beyond. So that's the limit. What about the -1? That limit turns out to be the unshearability limit. Do you know what the shear is? So take a deck of cards and put your palms at the top and the bottom, and you start sliding them against each other while keeping them parallel. And then the deck of cards, which used to be a rectangle, and deforms into a parallelogram, right? That's called shearing. And it turns out that at -1, you can't shear the material at all. That's the limit. Well, you can prove it by what is called a polar decomposition of any endomorphism, but you might have learned already to play with complex numbers. And you know that a complex number can be written in general as a product of something positive, that's the modulus, that's the size, times something that looks like e to I theta, which geometrically represents rotation. And there's a higher dimensional version of this in matrices, and it says that any square matrix can be written as unitary and Hermitian or orthogonal and symmetric. Or you can do it in pictures. Let's shear this like that. Well, you can do it in 2 steps. You can take this brown square and stretch it along the diagonal and compress it along the anti-diagonal to make what is called a losange or rhombus. Having made this, I can just rotate it in place, stonk by a small angle, and look, up to infinitesimal higher order errors, the result is the same as the result of shearing. So that's what happens. And you can see that when the Poisson ratio is negative, the first of these 2 steps becomes really difficult to do, because when I try to stretch it in one direction, the other direction also wants to stretch, and you have to fight this. And it turns out at -1, it becomes totally impossible, and that's the unshearability limit. So if you can't do the first step, you can't shear either. So in the analogy with waves, that means that there is another kind of wave which is called shear wave. You can kind of rub the material like that, and when I take it like this, the next bit goes like that, and it goes down, and then the wave travels like this, yeah? And that's called shear wave or S wave. And that means that at -1, the shear wave will travel infinitely fast, and that's not possible. Maybe I can insert one more digression. When you grow up in an earthquake-prone country like Japan, or maybe in California, we learn as children how an earthquake behaves. For example, I knew from, as far as my memory goes back, that when there's a big earthquake, first I'll be shaken horizontally. But then it stops, and there'll be an eerie calm. And some seconds later, a second wave will come and will shake me vertically. Yeah? So I have to be careful when the first wave comes and it's horizontal. By the way, just like in the case of lightning and thunder, by measuring the weight between those two waves, you can estimate the distance to the epicenter. But the reason there is a delay is that the P wave, this pressure wave, travels faster. So if, for example, Professor Matteo is the epicenter, which he usually is, metaphorically speaking, in many things, and he's sending the P wave like this, which shakes me horizontally, yeah? But a little later, a slower S wave, which departed at the same time, arrives, and which shakes me vertically like that. So you get shaken horizontally first and vertically next. So that's useful in earthquake measurements as well. OK, now, more modern stuff. This man is an aeronautical engineer from Japan called Mr. Miura. He's alive still, thank goodness. And in the 1970s, he invented and really made wonderful use of this fold pattern called Miura-ori. How beautiful is this? Now, I'll show you some examples of Miura-ori. You know how annoying it is to fold a road map. By the way, having said road map, I realize that probably most of the people in this room don't know what the map is. There used to be a paper object called map. Yeah? Yeah? It's not an app on you don't do this. You have to actually expand it and fold it. You know this? OK. There used to be something like this. And when you are driving, for example, from here to San Jose, and you don't know which way to go, and you open your map, and then OK. But that's OK. But when you want to close it, the map never falls back the right way. You start tearing here and creasing there and so on, and then there's a hole there eventually, and you go crazy, and next thing you know, your car is in a tree because you are not driving it. And this happens because the map folding pattern is really not smart. It has far too many degrees of freedom. But here's a Miura-ori, and when I want to fold it back, all I have to do is to put my hands and just press against each other, and it collapses automatically to a unique position. It has only 1 degree of freedom. Yeah? And when I pull, it expands. OK. And you can see that not exactly, not in detail, but statistically and kind of roughly speaking globally, it is behaving a negative Poisson ratio behavior. Yeah? Negative Poisson fashion. So that's what it is. And you can buy those things. So you should be able to buy those maps. And that's a map of somewhere near Tokyo. And you saw that this kind of uniqueness, which is very useful for folding, has to do with negative Poisson. And conversely, whenever you have something negative Poisson, it tends to have a very, very small number of degrees of freedom. We are not going to go into that, but that's really a beautiful and rather mysterious property. And I said that Mr. Miura was an aeronautical engineer, and one of the great applications was this. You know, a great challenge of satellite technology is that when you put the satellite in orbit, you have to have some source of electricity. What do? You expand and capture the solar light, the solar energy, by lots and lots of cells. But when you are at the launch, you have to package that into a very, very tight corner and put it in a compartment of the rocket. So once in orbit, how do you expand this? How do you deploy this? Well, usually what happens is it starts going in outer space, and it goes clonk, 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 and then gets stuck. Because joints get stuck because there are too many degrees of freedom, and you've lost billions of dollars of satellite. But what they did was to put this, fold this solar panel in a Miura-Ori. Then, mathematically, it's impossible to get stuck because there's only 1 degree of freedom. You just pull any two parts apart, and then it goes completely automatically. And if you want to put it back, you just compress those two things. It goes back, and absolutely no problem at all. So this was launched in 1997 on a satellite called Haruka. So far, we were discussing many properties of isotropic materials. Now, we already broached on the anisotropy, but I would like to discuss things that happen when you have direction dependence. And in order to do so, here is a little magic trick that I brought. Those two squares I cut out from a single sheet of paper in my office in the math department and put them together and clamp them. Now, I'm going to do this so that you can see it from the side, and the camera should capture what's going on for the web people. And when I hold these, there are two squares, yeah? Like this, they stick together. Of course, because they're made of the same material. In fact, they come from the same sheet of paper, so they sag the same way under gravity. Of course, they stick together, yeah? But when I turn them around, oops, just 1 second. What's happening? Just 1 second. I'm going to. This is strange. I'm going to do that. Excuse me. These are real experiments. So, so here it is. So they stick together, but when I turn around, they separate. Do you see that? In this direction, configuration, they stick together, but when I do that, they separate. But that's not all. This is the separating configuration. Okay. Now I'm going to let the clamp migrate to the next stage. It used to be supported here, but now it's being supported there. This was the separating side, but this time, supported on this edge, they stick together, whereas what used to be the sticky side, they separate again. Do you see this? So something is wrong. We thought of this because we thought that the paper is probably not isotopic. In other words, it probably has direction dependence. And because I like toys, this is a toy, but I brought a toy of a toy. If you fold a sheet of paper square into an accordion pattern like this, you see it can sag like this. It's very flexible in this direction, but in this direction, it becomes rigid. Well, of course, it's the principle of the corrugated surface, which is used all over daily life. But nonetheless, it's very interesting that in this direction, it doesn't bend, but in this direction, it bends. So what I did was to take out two squares from a sheet of paper, and I don't have to use a microscope to see how the microfibers are arranged and so forth. But all I know is that they are probably different. So in order to make the difference fight against the difference, I took out two squares, and when I superposed them, I rotated one on the other by 90 degrees like this. And now you see what happens in this toy model. If I support them on this edge, they don't separate because the rigid one is supporting the flappy one at the top, but when I rotate, of course, it's free to sag, whereas the rigid one sticks out. And when I go to the next edge, the sides exchange their roles. I'm pretty sure that this is what's happening. And the beauty of this is that, again, I don't have to know the microscopic structure. All I have to know is that it's not isotropic. And then I can take advantage of that in order to create something new. And another example, which is very much daily life, is this. Before the lecture, I went there to the public bathroom and harvested this. In the history of Stanford Online High School, this is probably the first time that the lecturer brings in toilet paper into the lecture. And I noticed that when I try to tear it like this, it goes down very, very straight, very nicely. I'll show you. So it went down nicely. But when I try to tear it like that, in the transverse direction, I simply can't go straight. I'm trying my hardest, but it goes zigzag, zigzag, and it becomes a mess. Yeah. So there is an anisotropy because of the paper is different this way and this way. You can see it like that. By the way, I couldn't help noticing at Stanford, the toilet paper tears much more easily this way than this way. And that's so you think about that. Okay. Okay. Now let's apply all of this consideration to geometry, and really highbrow geometry at that. Here is a funny question. Let's say you have a large sphere. That's a two-dimensional sphere inside a three-dimensional space. So sphere means spherical shell in the language of the mathematicians. Not inside. It's not solid. It has only the shell and spherical shell. Can you somehow or other put this large sphere inside a small sphere? Well, the answer is no if it's rigid, right? But suppose that it's kind of flexible. Can you put it inside? Well, how about, yes, you can. I can just shrink it. But that's too free. Let's do it isometrically. Isometrically means that if you draw various line segments on this sphere, all those line segments keep the same distance, the same length when I do the deformation. Or, a bit more pictorially, you can bend, but you can't stretch. Or you can, yeah? So can you, by bending, put a sphere inside a small sphere? By the way, if you have just a little strip of paper, where did my strip of paper go? Oh, I folded into a pentagon, didn't I? So if I have a strip of paper, you can certainly do this because I can just make a lot of wavy patterns on it. Yeah? I'm bending it. I'm not stretching anything. And I can put it in a very, very tight corner, right? But if I want to expand it, I can just pull it back. But can you do something similar with a closed surface, closed sphere? And the answer turns out to be that we cannot. Because something called the Gaussian curvature, curvature is, as the name indicates, a quantity, mathematical quantity that indicates how curved the surface is, gets in the way. It turns out that under isometric deformation that allows bending but not stretching, Gaussian curvature is constant. You cannot change Gaussian curvature. It's a conserved quantity in the language of physicists, if you like. And when you try to make something smaller, you have to dent it like that, right? But you see, along the rim of the crater that I created, it turns out that along the rim, the Gaussian curvature becomes 0. Whereas the sphere has positive Gaussian curvature to begin with and at the end. So you can't do this because you are going to violate the invariance of the Gaussian curvature. However, when you learn differential geometry, one of the most beautiful and useful subjects in mathematics, and you learn to compute the Gaussian curvature, you notice that there are two derivatives introduced. Yeah, you differentiate once and you differentiate twice in calculus. Two derivatives. So you can say, well, maybe we can try to do this deformation in a really sneaky way, which involves only one derivative, but not two derivatives. Let's use surfaces that have only once continuously differentiable, but not twice. This is really a subtle point. But the effect is that if somebody comes and says, oh, I can't put it in a small sphere because it's going to violate the invariance of Gaussian curvature, I can say, what Gaussian curvature? You can't calculate the Gaussian curvature because you have only one derivative. That sounds like cheating, but it attracted the attention of some of the cleverest people in the world. And Gromov and Nash is the beautiful mind Nash, discovered theoretically that it is possible to do this in C1 rather than C2. And more recently, about maybe 3 years ago, Borelli, Thibert, and so on, a French team, decided to write down an explicit sort of shrinking, isometric shrinking of a sphere. And this is the 3D printed version, approximate picture. You see that there are spirally kind of waves, that the creases that you have. But the funny thing about those creases is that when you zoom in on one of those wrinkles, each wrinkle is lined with more sub-wrinkles, and each sub-wrinkle is lined by more. So you have a scaled nested structure of wrinkles in a spiral pattern all the way down. And this is a typical example of what is called H principle. But anyway, what I noticed then when Borelli showed me this construction is that, all those really smart people worked hard to produce this, this construction. But instead of thinking hard, we could have asked Mother Nature to give it to us. I'd like to show you a nice buckling pattern. You remember buckling? Like that. Which is produced like this, and which hasn't been much studied. So I take a pair of glasses. Can you see what I'm doing? Yeah, OK. On a sheet of paper with some gap in between. Yeah, so this glass has a diameter, and there's a gap in between. And while holding it like that, I wrap the paper around those glasses that are facing each other with a gap. OK, I've just finished wrapping. And having done this, I twist those glasses against each other. I'm going to twist all the way and crease them anyway. And then what I manufacture is quite interesting. I don't know if you can see, the inside looks like this. OK, maybe it's not so easy to see. But when you unfold, it looks like that. Can you see? Maybe it's white. There's a white dot. You can't see really. OK, I'm going to try to produce some shade effect. From the other side, is that better? Yes, you can probably see a little better, no? Like that, yeah? OK. So you have a very kind of beautiful zigzag pattern that is produced automatically. Again, I didn't have to think. Nature took its own course. And all that geometry is determined by one dimensionless parameter. That is the ratio of the gap against the diameter. And you see, this kind of zigzag pattern looks very much like the Minori. And for a good reason. What did we do? We had this sheet of paper, and we asked nature to put it in a smaller space. But by twisting, all I did was, my only input was, please twist and put it in a small space. And nature responded, has to find a solution, and that was her solution. And it's isometric because paper can't be stretched. So that's what is going on. So you produce a nested version, and physically you can do this H principle by putting some kind of descent algorithm. Anyway, that's my guess. OK. Now, another example that I would like to show, the last one before we say goodbye, is this one. This was invented by a Japanese engineer, again, Mr. Momotani, about, I think, 40 years ago. And it's known as Momotani carpet. And this is a small variation on this. I folded this particular example on a long, long flight to South Africa, where I go and do charitable work, as Professor Matsuo mentioned. So there's a long, long flight from London to Cape Town, which takes about 14 hours. And on that journey, I folded this. It started from a sheet of paper about a year large. And as soon as we took off, I started folding this. By the way, I didn't fold for 14 hours nonstop, of course. I rested, and then, there's also even a coffee stain here while I was resting and so on. But you can imagine the worry of my neighbor. I started folding and so on. Can I change my seat, please, and so on. OK. Anyway, so this is made from a single sheet of paper. And when I pull, please watch what happens. It does this. And what is cute is that on the other side, what's happening is perpendicular to or dual to what's happening in front. Yeah, so it's a really fantastic thing. And you notice that it's negative Poisson again. Yeah? When I pull, it expands in all directions. But not only that, it comes with an additional bonus that I was not expecting. This is a sheet of paper. Sheet of paper is not like rubber. It's not particularly elastic. But this gadget, this object that I have folded, has an effective elasticity. Look, when I pull and release, it bounces back. It's bouncy. So here, you have accidentally, serendipitously discovered a way of making something rubber-like out of a sheet of paper. Yeah. And if you are interested, later on, I'll discuss possible sort of medical applications of this kind of thing. But let's move on. So we'll summarize this by discussing some general properties of Poisson ratio. And here is a primitive example, which was folded by Wei at Harvard in those days. And that's and let's, in order to simplify the formulas, assume that this Miura-Ori, which appears all over the place, happens to have each facet a losange. In other words, all the edges have the same length. It doesn't have to be like that, but the formulas will be more complicated. With that convention, the state, or if you like, the condition in which Miura-Ori exists, can be characterized by two angles. One of them is geometric, that's alpha, which shows what kind of shape that facet has. If alpha is 90 degrees, each facet is a square, and if alpha is very small, each facet is long and thin. And the other one is dynamic angle, theta. Theta is the angle between the two neighboring facets. So if theta is very, very close to pi, the whole thing is almost flat out. And when theta becomes small, the whole thing starts being folded back. Yeah? Okay, generally changes. So with the shape alpha and state dynamic parameter theta, in that state, the Poisson ratio turns out to be this, 1 minus that. Now, don't pay too much attention, but you see it's a product of signs, and sign is always less than 1. So if you take this product of signs and take the power -2, it's going to be larger than 1, right? And I'm subtracting that from 1, so it's going to be negative Poisson ratio. Congratulations. But there's something else. You see, by changing the values of alpha and theta, you notice that this Poisson ratio alpha can hit any negative real number, all the way from 0 to -infinity. So not only is Miura-Ori an example of negative Poisson ratio structure, but it is in some sense a universal giver of any negative number as Poisson ratio. So it's a really robust machine, if you like. And here you might object, but we had this theorem a long time ago, didn't we, that the lower bound for Poisson ratio was -1, but that was the isotropic case. This is anisotropic, that is very direction dependent, so that can violate that bound as well. So there's something else, another universal property of Miura-Ori. We discussed a number of times this concept of buckling, but that was a one-dimensional buckling. You know, you had a rod and I compressed it, and so on. Let's do a 2D version. What does it mean? So I imagine a membrane, and at each point of the membrane, I apply a homogeneous compression, uniform compression. How do you do that? Well, it's actually quite difficult, because if you try to press the edges of membrane, you know, the boundary effect becomes very significant, so it's not very good. So the best way probably is to use moisture, or maybe to use temperature in order to compress the whole thing. But anyway, if you apply a homogeneous compression, well, for a weak compression, the whole membrane shrinks elastically, so it stays flat. You can barely see it with your eyes. But at some critical load, the membrane can't take it and buckles into the third dimension. And believe it or not, the buckling pattern is the Miura-Ori. So Miura-Ori is the lowest energy buckling pattern over two-dimensional buckling. So far from being a special example of negative Poisson, Miura-Ori is actually the simplest and universal model of negative Poisson ratio. You can ask nature to do this. But then, at this point, I realized something else. You know, we have been very clever, so to speak. I mean, designing this and designing that, figuring things out. But there is actually a very, very easy way to produce a negative Poisson ratio material. You don't have to design any of this. What you have to do is take a sheet of paper and then do this, for example. And watch what happens when I try to open it. It starts opening in all directions at the same time. It's negative Poisson, isn't it? Of course, because I made it this way, I compress it from all sides, and so when I undo it, it's going to expand into all sides. Now, those people who are attentive, that's everyone in the room, will probably notice that I'm cheating a little bit, because if with bird's eye view, we see that it's negative Poisson. If I see it from the side, when I compress it, something that used to have 0 thickness now has some finite thickness, so it expanded in the third dimension. Yeah? But that, so it's not strictly speaking negative Poisson in that direction, but that difficulty can be circumvented because I can make lots and lots of waves, and more waves I put, more creases I put, the narrower that gap is going to be. So I can make that as thin as possible, as thin as you like, so it's essentially negative Poisson ratio behavior. Anyway, so randomized fold seems to produce negative Poisson. So I have a conjecture. A bold conjecture, which is written in bold characters here. You see, people until recently thought that the Poisson ratio has to be positive and said, well, negative Poisson ratio structures don't exist. And then some people discovered negative Poisson ratio behaviors. But that's a very, very special corner of science and engineering. Really sort of clever people can do this, but not the rest of us. But it might be that You see, this looks pretty random, doesn't it? Of course, it has to satisfy that geometric condition about the sum, alternate sum being 0 and so on. But apart from that condition, it's probably very, very as close to random as any object that we can create. And if a random object like this has negative Poisson, I conjecture that maybe among all the structures in the universe, the majority of them actually turn out to be negative Poisson. Not the freakish counterexample, but actually the majority case. It's time to bring this to a close, and because we started with some kind of numerology, let's play with numbers again. You know, a lecture like this is supposed to last for 50 minutes, and I lasted for 55, and that's 3,000 seconds, 3 times 10 to 3 seconds, right? Now, do you know how many seconds there are in a year? Huh? Do you know? So some people I hear something. I use this conversion whenever I do astronomical calculations and so on. It turns out that 1 year is almost exactly pi times 10 to 7 seconds. That's the second present that you can take home today. And you should go home and do the arithmetic. It's amazing. The error is less than 0.4%. In case some people knew about pi times 10 to 7, and there's an even better approximation, which is square root of 10 times 10 to 7. So in other words, 10 to 7.5, and then the error drops to less than 0.25%. Okay, but anyway, that's about 3 times 10 to 7. So by multiplying this by 100, you see that 1 century contains 3 times 10 to 9 seconds, 3 billion seconds. Well, but one lecture is 3,000. If you divide one by the other, and that's the last present that I would like to give you to take home, one lecture equals 1 microcentury. 10 to minus 6. So from now on, when you go to a lecture, when you sit in front of some people, some screen and so on, and you are attending a lecture, you can say, I'm going to invest a microcentury. It's been a pleasure and privilege to address this select audience, which I owe to Professor Matsuo and Dr. Hoshi. Thank you very much for your company in the last microcentury.